when we find the derivative of?
Yes, yes. Thank you very much. Indeed, f prime of x, that's what it is. We know that the slope of the tangent line to the graph of a function is f prime at that point. Yes. Excellent. Thank you. Good. So now I'm also going to use the rise over run. Okay. So I'm going to create this right triangle. And here's the rise. And you'll tell me in a moment what it is. And here's the run. Well, we already have it. It's dx. So then the rise is something you will tell me in a moment. And the run is dx, clearly. That's no secret there. Okay, so now let's think for a moment. What can I put here? There is only one thing that fits in that spot.
dy.
Of course. Of course. There is nothing else. So this piece is dy. Now, of course, you're going to say, what does dy mean? Well, see, whenever we have an error in x dx, it translates into an error in the function value. Because if q is right here, there is no error. But if q is next to p, there is an error. This error in x creates an error in y. This error in y is the delta y. Because it's the exact, and I'm using the function. What is it? F of x plus delta x minus f of x. This distance minus this distance gives me this distance. But now I'm using the tangent. By using the tangent, I'm using the derivative. If I'm using the derivative, this is now dx, and this must be nothing else but dy. Okay, I'm going to take this graph again to explain what I'm just showing you. So here was our function. This is point P. This is point Q. This is the error called delta y, and this is the error called delta x. This is the f of x, and this is the f of x plus delta x. So delta y is the exact error in f of x created by delta x, the error in x. What does it equal to? F of x plus delta x minus f of x. So I have to write delta y. Delta y equals f of x plus delta x minus f of x. Now, if I use same thing, I just copy. If I'm using the slope of the tangent line, then this is dx, and this is dy. So what is dy? Dy is the approximate it's not the exact. the approximate error in f of x found using f prime of x. And it's called the differential of y. So, coming back to my first graph, I want to determine a relationship between the exact error in the function and the approximate error in the function. Keep in mind that Q is right here, very close. What will you say would be, my drawing is confusing because I'm zooming in, but remember Q is very, very close. What will be the relationship between the exact error and the differential of y, the error that is an approximation of the exact error using the derivative? What could be the relationship between these two? Keeping in mind that Q is right here. What do you think, these two? What will be the relationship between these two? You cannot say that they are equal. It's not possible, unless it's a very special case. You cannot say that this is bigger than this. You cannot say that this is bigger than that. So the inequality symbol will not work. The equal symbol will not work. What symbol do I have to write in here? If dy is the approximation of the exact error, what symbol? There is only one symbol that I can put in here.
This is like the
approximate symbol,
yeah.
Of course, of course. That's the word, the key word here. Although you can say from the graph, no way, look how big this is, and look how small this is. True, I zoomed in, but they have to be very close to each other. They are approximately the same, but never, almost never equal. So I'm copying the formula for this, but I will copy it with dx. So f of x plus dx minus f of x is approximately, and now let's look at this one. Can anyone solve this equation for us for dy? I'm going to write it here again. I didn't want to write that. F prime of x equals dy over dx. Can anyone solve this equation for dy? This equation for dy. And tell me what to write. And whatever you tell me, I'll write it here, because dy is on this side. On this side, I have f of x plus dx minus f of x. On this side, I have to have dy. Can anyone solve this equation for dy?
F prime of x over dx.
Times.
No, times.
Very good. That's it. That's it. And now I'm going to move this here. From one side to the other, I change its sign. And now I'm going to show you examples of where this is used. Super important relationship. And we'll have word problems with this, but also a numerical example. I want to show a numerical example before we move on. Okay. Any questions? Before we look at an example, however, I want to say one more thing. Please give me any function you want, any function.
2x plus 1.
Okay, so we created a function, and we want to understand the difference between the derivative of this function, which is denoted by f prime of x, and the differential of this function, which is denoted by dy. Can anyone tell us this answer? And then can anyone tell us this answer?
It's just 2.
Excellent. And here? Okay, let me show you the formula again.
What is that, dx?
That's it. So thank you so much. Please understand the difference. This is a crucial situation. If I'm asked to find the derivative, I write this. If I'm asked to find the differential of this, I have to write the derivative times dx. One more time, let's write it here. dy equals f prime of x dx. Please remember this very, very important concept. When we need the derivative, we do this. When we need the differential of a function, we have to write f prime of x dx. If the function has p in it, then it would be dy f prime of p dp. If it has w in it, not x, dy will be f prime of w times dw. So whatever the variable is. So now I would like us to illustrate with an example on page 341. So let's choose. I'm sharing my screen. Where is my book? No, don't.
Professor Lead,
Yes.
a bit off topic, but I was just wondering if the test is still next Thursday.
I doubt, because I don't know if I can finish tonight. If you remember, we always have to have a full review.
Yes, ma'am. So what do
session.
you think the following Tuesday?
So I don't think I can finish tonight, but we'll see.
Yes, ma'am. Thank you.
Thank you. Of course, we always have to have a full review. Okay, so right here. And then I said 341. Will it open or am I logged out? Okay, 41. Okay, so let's illustrate with a numerical example, and then we're going to look at word problems. We're going to select a word problem. So first, a numerical example. So I'd like to look at 13 through 18. Please choose.
17.
17. So let's look at 17. We have the cube root of 1005. Perfect. So we are trying to approximate this. And the moment I'm asked to do that using differentials, then I will write my formulas. And this is the only one I need. And you can say, how is this related to that? In a moment, you'll see. So let's take a look at this and identify a function. Which function, when you look at the cube root of 1005, which function do you think it's applied here? Is it exponential? Is it log? Is it a ratio? Is it a product? Is it, what is it? What function is applied here?
Exponential.
The exponential looks like this, a to a power, a number to a power.
Wouldn't that be 1,005 to like 1/3?
You could consider that. You could consider that, but how do I read it first? The cube root of 1,005. What could be the function that I'm looking at?
Quadratic?
It's the cube root. I just read it, right? The cube root. So it must be the cube root of x. This is the operator applied to this number, right? We identify by simply reading it. And I read the cube root. So it must be the cube root of x. What if I say natural log of 5? Which function is applied now?
The natural log of x.
The natural log of x. What if I say 1/2? Which function is applied in this case?
A rational function.
1/x. What if I say the square root of 3? Which function is applied in this case?
Square root of x.
That's
The
it.
square root.
That's it. The square root of x is applied to 3. 1/x is applied to 2. Natural log x is applied to 5. So the function here is the cube root of x. Do we understand that? That's the first step and one of the most important. Is it clear how we identify that this is the cube root of x applied to this number?
Yes.
Excellent. So I identified this piece. So that's done. This is here. And f prime, I can immediately say this is indeed 1 to the third. So it's this situation. Yes, you could say that, but this is your x and not this. So that's why this is not an exponential, right? Because the variable is the base, not the exponent. So let's differentiate. F prime of x, I bring down 1/3 and I subtract 1 from the power. So from my formula, what do I have so far? I have this. I have this. What is next? I have to identify x and the little bit of error. Okay, so now let's see. Looking at 1,005, what do you think is x? And what do you think is the little bit of error? Once I identify these two, I'm done.
Is the 5 the error?
The 5 is the error. How do I know? Because I can take the cube root of 1,000, and that's the closest. So how much is x then, if the error is 5?
1,000.
1,000. We're done. That's all I needed to identify the function, find its derivative, identify x, and identify the little error. So now I know the answer. So let's do it. I'm looking at my video here. Yep.